Perfect. Okay. Welcome everyone to the second MCRN AIM Research Community Colloquium. Today our speaker will be Roland Welter. He's a postdoctoral researcher at the University of Hamburg, currently doing a position with the TRR 181 project. He received his PhD from Boston University in May 2021. And today he'll be giving us an overview of the mathematical results regarding atmospheric convection. And so with that, I'll let you take it away.
Okay, thanks, Christian. Yes. Yeah, today I'm going to talk about some recent work that I've been doing here at Hamburg as part of this collaborative research group, the TRR 181. So I first wanted to begin with some context for the kind of motivations for this research, coming from the atmospheric sciences. So what I wanted to convey here is what they do in atmospheric research is discretize the entire Earth and represent the entire atmosphere as some kind of discretized PDE, where we have all these grid cells, and these grid cells are you represent them as being units of fluid with some constant velocities and temperature, pressure, and so on. And this you might kind of model the atmosphere with an equation like this, where this is the kind of Navier-Stokes evolution for the velocity, and we have a Coriolis force and a buoyancy force. We have the temperature equation, incompressibility, and you couple these kind of variables for each box together by a discretized version of this PDE. And this is actually kind of too much for most computers. This third component, what they actually in practice do is use some scaling arguments to say that, okay, if we had some typical velocity, typical time scale and length scale and so on, then these terms should be small. And so they just throw these terms away. This is kind of what they say here is that this is in approximate hydrostatic balance. And while these terms may be small, it's of course not truly accurate to just throw these terms away. So what climate scientists then do is add in some additional terms that represent some kind of effect of these other terms without including their full evolution. So if we had a fully 3D Navier-Stokes model, this would be very numerically unstable and difficult to work with. So this adding in new terms it kind of still preserves this nice two-dimensional type flow, but also pushes the model back to reality. And this is called parameterization. And we in the TRR are especially concerned about energetically consistent parameterizations. Basically, can we find some terms to add back in so that we aren't having different behavior for the kinetic energy and potential energy than in the full model. That's kind of where my problem begins. And I've been looking at rotating Rayleigh-Benard convection as a model to understand what's being lost when we throw away these terms. So in this model, we have our Navier-Stokes, we have a Coriolis force, a buoyancy force, and temperature equation. And so we are going to see kind of a convective flow. We're going to heat the fluid from the bottom and cool the fluid from the top. And then the buoyancy force will drive some kind of turbulent convective flow. And for simplicity, we'll assume that it's so-called 2.5 dimension, so that the velocity has 3 components, but the variables only depend on 2 spatial variables. In this model, we have a few non-dimensionalized parameters. The first is the Prandtl number, which describes basically what fluid you're looking at in the sense, and so it's the ratio of the viscosity to thermal conductivity. And then the other, probably most important physical parameter is the Rayleigh number, which is a measure of how turbulent the flow will be. So it's the temperature difference between the top of the bottom of the fluid and the top, times some volume factor, times some other factors. And if we take the physical parameters to be some representative numbers from the atmosphere, like so, then we'll see that we are interested in a Prandtl number around 1 and a Rayleigh number around 10 to the 16th. This large Rayleigh number is really kind of the challenging aspect of modeling this sort of flow, because it's very turbulent. The quantity that we're interested in is the vertical heat transport. So this is the vertical heat transport that we're interested in. The Nusselt is the Nusselt number. This is defined to be the average vertical heat flux averaged over the whole domain and averaged over infinite time. And this Nusselt number, it depends on what flow you're looking at, as what solution of the PDE as determined by the initial conditions, as well as the parameters, Rayleigh number, Prandtl number, and so on. And this quantity, there's a lot of open questions about it. There's a lot of numerical studies and experimental studies, but relatively few results proven analytically. So one such result that exists is this kind of upper bound, which says that the supremum of the Nusselt number taken over all possible initial conditions scales with the Rayleigh number as a 5/12 power. So this is a fairly nice result because you could use this in theory. You could use this to assess whether your numerical climate model is reporting an unphysically high heat transport. So say you have some parameterization and you run the simulation, you measure the heat transport, and if you get some number which is above this, then you know this is an inaccurate climate parameterization. But I should say that even if this this upper bound on the Nusselt number was sharp, it may not be useful to climate scientists because of exactly this supremum. The supremum should apply to dynamically unstable solutions as well. So it is necessarily a very kind of rough estimate. So to motivate the approach that I've been taking, I first want to talk about the reduction of the PDE to an ODE model. And the simplest way that this can be done is first, if you subtract off the linear temperature profile, which kind of is just linearly interpolating between the bottom and the top with this new variable theta. Then if you Fourier expand the stream function and theta in kind of the coarsest way possible, only the largest scales, then you end up with this Lorentz system, which is so well known. Then to give you a feeling for what's going on here, I've plotted the temperature profile in this colored graph and the velocity profile. And as if we look at a simulation of this model, then as you move along the trajectory, the fluid flows around, and you're only seeing these kind of large convection rolls, the largest scale motion of a PDE. And so at this low Rayleigh number being the temperature, kind of, you can think of it as the temperature difference. If there's not a big temperature difference, then eventually the fluid settles down to a fixed point solution, which is representing a constantly overturning large scale flow. And that's kind of more or less for this low Rayleigh number. This is kind of the behavior that you would expect of the full PDE captured by this reduced system, at least for very small kind of low Rayleigh number, low thermal force. So then let's look at how the heat transport works in this very simple Lorentz model. If you look at the Lorentz model, then the reduced version of the Nusselt number becomes this time average. And if you begin from a random initial condition and let the flow evolve for some time, then for 0 Rayleigh number, you just settle, this time average is 0 because you just settle, wherever you begin, you settle down to the 0 state. The origin is the global attractor. But when you increase the Rayleigh number, then a pitchfork bifurcation occurs, and you see the heteroclinic orbit from the origin to these now non-trivial fixed points representing the constantly overturning solution. And so for these higher Rayleigh numbers, wherever you begin, you end up going to one of these non-trivial solutions that have non-zero heat transport, and these increase in their heat transport, and the global attractor is now some more complicated object. So this continues for some time, and then eventually actually if you increase the Rayleigh number high enough, then the fixed point solutions lose stability, and then we see that the global attractor is this complicated fractal that's quite well known. So here, what's interesting is that when you now begin from a random initial condition, you end up, so the solutions end up following this attractor, and the heat transport that you observe on this attractor is visibly less than the heat transport that you observe in orange here on this, that are given by the solutions exactly on these fixed points, these constantly overturning solutions. And so this is one aspect. So right away, we can see that an upper bound of this kind is not really what we want for analyzing the climate. And also, we can see that the chaotic behavior is transporting less heat than a constant overturning rate. This is because the fluid is using more energy, kind of moving around in a turbulent way than it would then would be transported if it were in some kind of nice regular fashion. Okay, so this is kind of the lessons that I wanted to point out for the Lorentz model. The problem is, of course, that the Lorentz model is way too large scale to really represent some kind of turbulent flow that's relevant for the atmosphere. So so I want to generalize this process of the Lorentz model and see if we can aim for some of the same results, analogous results. So first, in order to generalize this procedure, we need to find a general expansion for the velocity field and the temperature deviation. So for the temperature deviation, this is just basically a standard Fourier series. You can, for L2 functions, you can just expand in sinusoids, although they need to satisfy the boundary conditions. So the sinusoid that is representing the vertical variable it must be sine. The velocity field, the general Fourier basis is a bit more difficult to find. You could expand each component of the velocity field in a sinusoid, but because of the divergence-free condition, the components can't be chosen independently. So you have to do some work to show that these four types of vector fields are everything. This collection of vector fields forms a complete basis for this L2 space of divergence-free vector fields. So these are just some normalizing factors and so on. So we've found a general basis, and then what we want to do is study a truncated model, just as in the Lorentz system. So we study a truncated velocity field and a truncated temperature deviation, where these sums are taken over just some finite index sets rather than the infinite index sets that would be for an L2 function. And we then define, if we have some index sets in mind, these index sets are going to be themselves indexed by a parameter m representing how large is this index set. And we then define some projection operators so that we consider the projected problem, where we just take the PDE and project everything onto this finite basis. And then in order to figure out what is the ODE that the PDE corresponds to, we take each element of our basis and we compute an inner product of the PDE solution with, or a PDE equation with each one of our basis elements. And then we get a system of ODEs for each wave number. And so we can do this explicitly, and then all of the linear terms are quite easy to compute. Here we've got our viscosity terms. We've got a buoyancy coupling between the velocity and temperature, Coriolis force, and then the nonlinear term, which the nonlinear terms are quite difficult to resolve explicitly, but in the end, it's just computing some integrals of a large number of cases of sines and cosines and stuff. So these can also be explicitly resolved. And what's important for us in choosing our models is the energy consistency, like that's the goal of this TRR. And the energy balances that are implied by the PDE are as shown here. This first energy balance represents the time evolution of the kinetic energy. The time evolution, you see here a dissipative effect of viscosity, but you also see that the kinetic energy can increase due to the buoyancy coupling. And also here's the balance of potential energy. And this also, you see this cross coupling between the buoyancy due to the buoyancy force. And then we've got vorticity and temperature fluctuations. So we would like that our ODE models satisfy these same balance laws as the PDE. It actually turns out that not any random choice of Fourier modes will guarantee this. You have to specifically satisfy certain mode selection criteria, which are given here. And with these mode selection criteria, any model that satisfies them will preserve the energy balances so that this truncated kinetic energy will obey the same equation as the kinetic energy balance for the full PDE, and so on. So to illustrate what this criteria looks like, I have here the first. I should say this then creates a hierarchy of models where we look at increasingly large index sets, and the ODE corresponding to this sequence, the ODEs corresponding to the sequence of index sets is called the HKC hierarchy, Howard Krishnamurti Coriolis, after some people who first were studying energy consistency in mode truncated models. So the first model is actually just the rotating version of the standard Lorentz model. Here you attach this Fourier mode 1, 1, which is exactly here. Now, in order to satisfy the energy balance, you are required to attach then this mode and these modes. So yeah, here we've got our Lorentz model. It represents only large scale motions very well. Now, if you follow the next step, you attach another Fourier mode, and the energy balance requires that you then attach these two modes. You get a larger system of ODEs, and then you can represent more complicated flows. And so this procedure, we generalized it so we can do this as much as we like. Then we get some very large system of ODEs, but that's okay because MATLAB can handle that. Okay, so then I did a number of theoretical results kind of to support a number of numerical studies that we did in studying heat transport. The first was just a kind of classical existence uniqueness theorem, which is that this system or this hierarchy of ODE models, it's bounded and in some spaces, and so in some compact space, so you get a subsequence which converges to a solution. So you have solutions to the PDE. So that's good. And then you also have a maximum principle, which is very nice. So you have the temperature is equal to some theta bar plus a fluctuation, where this theta bar is bounded in L infinity. This is like you're forcing the temperature at the boundaries, and this theta bar remains between the boundary values. And the theta tilde is some initial fluctuation, which decays exponentially. So you have a maximum principle in this way. And then lastly, there is an absorbing ball for this for these solutions. So any solution eventually enters this absorbing ball in H1. And so then this proves that there's a compact global attractor for the PDE, not just the Lorentz ODE. And now I just wanted to say a brief word about what does this existence theorem really mean? So this theorem says that if you have any time and any epsilon, then there exists an M star such that for a sufficiently large enough ODE model, you have this type of convergence. So the L2 norm integrated over time of the true solution minus the ODE approximate solution is less than epsilon. And if we're thinking about trying to use this existence theorem to study the Nusselt number, which is an infinite time average of this U3 times theta, then this says that this infinite time average should be well approximated if M is chosen sufficiently large. But this existence theorem doesn't actually say what M star is, so it's not really useful for computations, because it just says that eventually, if you choose a high enough model, you'll have a good approximation, but doesn't say how large it should be. That's why I'm kind of trying to study these questions theoretically. There's a really nice set of results in the area of reaction diffusion equations around this this type of thing, which is if you can prove the existence of an inertial manifold, then you have kind of the explicit M star that you would want, which gives that this finite ODE approximation actually captures the full dynamics, and you have exponential decay of the true solution from your with only approximating with your finite dimensional ODE. But this is still not known whether this can be done for Navier-Stokes type equations. So the result that I proved instead was just the analog of the results of Temam and others that estimate the dimension of the attractor as increasing by some linear function of the Rayleigh number. And so this just gives you not a proof, but just hopefully some idea about how large you should choose the ODE models. And then on the other hand, I studied the bifurcations at the origin to get a lower bound on the dimension of the attractor, since part of the attractor is the unstable manifold of the origin. And so here we just see some pictures which indicate how the bifurcations of the origin work. These different curves represent critical curves for different Rayleigh numbers. And when one of these critical curves crosses one of these Fourier modes, then you see a bifurcation occur. And this, when a bifurcation occurs, the unstable manifold of the origin increases in dimension. And so then you get this lower bound by studying how many of these bifurcations occur at a given Rayleigh number, and you get this lower bound, which is a 1/2 power of Rayleigh number. Okay, and then I did some numerical studies. Here's just a simulation of the temperature field for a high-dimensional model. I looked at the convergence in time, and most often the convergence of the Nusselt number in time was as shown in this blue curve, where it just converged rather quickly to some value with small fluctuations. But there was also another scenario which I observed, which is if the initial condition by chance started near some fixed point, unstable fixed point, then the Nusselt number appears to converge to some value, but eventually converges to some other value. So you just have to be careful about how long you integrate the solutions. So I did a numerical study of the Nusselt number at many different Rayleigh numbers and rotation numbers, and across many different HKC models, and saw this type of behavior where we have the higher dimensional HKC models were able to transport more heat than the lower dimensional ones. Basically, the low dimensional models, eventually the thermal forcing overwhelms the viscosity, and then the fluid just moves really quickly. But this doesn't increase the average rate of heat transport, because the heat is transported up and down just faster and faster. And so it doesn't produce any more heat transport. But in the real fluid, you see more heat transport because the fluid uses finer scales to transport heat in a way that is not possible in the lower dimensional models. And so I just tracked using the highest dimensional system as so the supposed truth. I tracked the error of each model, and when the error became outside of 10% of the value reported from the highest dimensional model, I reported that the dimension was too low. So over here we see in blue the minimal required dimension for staying within this 10% boundary. And it actually tracks very well with the lower bound that I got from the theoretical arguments here depicted in red. Lastly, I did a bifurcation analysis, bifurcation diagram of a of the Nusselt number in the HKC 21 model, which I chose in this range of Rayleigh numbers because the HKC model still, HKC 21 still lies within this error threshold. So it should be a good approximation for the PDE. And here's what I saw. And so here we have unstable fixed points in red, stable fixed points in blue, stable periodic solutions in purple, and unstable periodic solutions in orange. And then some solutions beginning from random initial conditions in green. And so the random initial conditions, well, okay, so first of all, there are multiple stable values of the Nusselt number, apparently. And so the time averaged, or I mean, the random initial conditions in green seem to be flipping back and forth between the stable values of the Nusselt number. And I think that this is an interesting and possibly challenging finding for the climate scientists who want to treat convection as a subgrid process. But I think that it's kind of challenging to do so because if there are multiple stable multiple stable Nusselt numbers, then which heat transport will be observed is dependent on which solution the it depends on the subgrid quantities of exactly how the flow is going. So yeah, I'm still thinking about this problem. But yeah, that brings me to the end. I've put all this MATLAB code on GitHub, so it's freely available, and then some ideas for current work and future plans are shown here. And so, yeah, thanks for your time.
Great. Thank you, Roland. That was a great talk. And also thank you for, once again, for doing this so late your time in Germany. We really appreciate it. We have time for some questions. If anybody has any they'd like to ask, please go ahead.
Oh, can I ask it? So would you be willing to conjecture on the basis of these numerics that the attractor grows like the dimension of the attractor grows like the square root of the Rayleigh number?
I'm not sure about that. I would guess that it does not, because this local analysis that you can do at the origin says nothing about what is there can be many global bifurcations or just local bifurcations that are occurring elsewhere, for instance, on these fixed points that are always emerging from from the attractor. And yeah, I have no idea about the rate, but I just maybe a cynic or something, because I think that yeah, the attractor is probably really complicated, and the worst is possible, maybe.
I was just thinking, you had these numerics where you looked at, for a given Rayleigh number, how large of a model did you need to choose to accurately reproduce the heat transport? And there it did kind of seem to track like the square root, if I understood. So
Yeah, but I think this might just be because I was only looking at small Rayleigh numbers, and
okay.
I think
Yeah.
if moving into higher Rayleigh numbers, I don't know. Yeah,
Yeah. Fair enough. So,
yeah.
Okay. Any other questions for Ron?
May I ask a question?
Yeah.
So, I mean, so it all relates to the dimension of your manifold M to see how well your approximation is, right? So far, what you have been doing is you have been relying on, so the question was that you've been looking at how big do you choose M, right? So there is no way to establish a lower bound that's good enough. And so is there any other methods that besides what you have presented that you know that's out there that to kind of get a good approximation of the manifold, like to get a good lower bound on M? Is there any other methods that you could use besides looking at the Rayleigh numbers, and also besides looking at the Nusselt number? Like, is there any other like methods that you could use to get a good approximation, to get a good lower bound?
Yeah. Kind of this approach that I was mentioning about inertial manifolds really seems to be like, if it could be done, it would be everything that you would want. But it's just so I a little bit skipped over this. The method for constructing an inertial manifold, it relies on there being a spectral gap between this eigenvalues of the Laplacian, or well, eigenvalues of the linear evolution. And this needs to be larger than the Lipschitz constant of the nonlinear term. And if you can show that, then what's basically going on is the viscosity at that scale is so strong that no matter, or that the cascade of energy into that small scale is weak in comparison. And so then basically that scale is nothing important is going on in it. And so so that's the problem, is that for a two-dimensional model, the spectral gap is just a constant. So it's not clear whether you can do it. And if you can't do it with this spectral gap argument, then there's other things you can do, but they're like way more complicated. So it's possible, I would say. It's possible.
Okay, thank you.
Great. Any other questions for Ron? If not, I had one small question. Would you mentioned you were doing all of this in MATLAB, and that of course can be kind of a computational constraint. Do you think that you'd find any benefit in exploring these ideas if you had more computational power, or could do something like parallel computation?
Actually, yeah, that was one of the things that
Oh.
I also skipped over was that I just did all these computations on my laptop. So my what I'm working on now is trying to redo these computations on a supercomputer and see if I can push the boundaries.
Oh, okay, interesting. Yeah, I'll send you an email. I know of a software package that is supposed to help make that easier. I don't know if it would apply, but I'll shoot you an email.
That would be great.
Okay. Okay. Any other questions? Okay, well then, thank you again, Roland, and let's see if I can find the clapping hands there. Appreciate the talk and appreciate the time. And
thanks everyone for coming.
yeah. And of course, we'll post this to YouTube if anybody wants to review it again, and then see you all next week. Right.
Okay, bye.
Thank you.
Bye.
Bye, everyone.